Let's start with the magnetic half. We're going to go over the basic rules of the road for how all magnets work.
Okay, so every single magnet you've ever come across, from that little one holding up a drawing on your fridge to a massive industrial one, it has two distinct ends, a north pole and a south pole. It's a lot like how electricity has positive and negative charges. These poles are where all the action happens.
And the number one rule is something you probably remember from science class, right? Opposites attract and likes repel. So a north pole will always try to get to a south pole, and if you try to push two norths together, they're going to push each other away. It's simple, it's predictable, and it's a super powerful interaction.
But this brings up a really interesting question. With electricity, we know you can have a positive charge all by itself or a negative charge all by itself. So can you do the same with a magnet? Could you have just a north pole with no south, or just a south with no north?
Well, the answer, as far as science can tell us, is a big nope. These things, called magnetic monopoles or single poles, they just don't seem to exist. If you take a magnet and snap it in half, thinking you'll get a separate north and south, it doesn't work. You just end up with two brand new, smaller magnets, and each one has its own north and south pole. And this right here is a huge difference between electricity and magnetism.
All right, so we know magnets have this invisible force field all around them. But how can you actually see something that's invisible? It sounds impossible, but it turns out there's a pretty simple little tool that lets us do just that.
And that tool is a compass. What's so cool about this is that a compass needle isn't just a piece of metal. It is itself a tiny little magnet. It's balanced so perfectly that it can spin around freely and line itself up with whatever magnetic field it happens to be in.
So, by moving this little compass around a bigger magnet, we can actually trace the shape of that invisible field. It's pretty neat. If you put the compass near the magnet's north pole, the needle points away from it. Then, as you kind of slide the compass along the side, you'll see the needle follow this nice curved path. And when you get all the way over to the south pole, the needle flips around and points right at it, following that opposites attract rule we just talked about.
And here's the key takeaway from that little experiment. When you trace out that whole path, you find something amazing. These magnetic field lines aren't one-way streets. They flow from the North Pole to the South Pole on the outside of the magnet, but then they continue inside the magnet, going from south back to north. They form a complete, unbroken, closed loop. It's like a racetrack with no start or finish. Okay, now let's take this whole idea and scale it up. Way up. Because the single most important magnet in your life isn't holding up a grocery list on your fridge, it's the actual planet you're standing on right now.
Yeah, see, the source of Earth's gigantic magnetic field isn't some giant bar magnet buried in the ground. No, it's generated thousands of miles beneath our feet, deep, deep down in the planet's core.
So, picture this. Way down there, there's a core of molten liquid iron and nickel that's just churning and flowing around. All that moving, superheated metal creates massive electric currents. And what did we learn at the very beginning? Moving electric currents create magnetic fields. This whole process is called a dynamo, and it literally turns our entire planet into one giant electromagnet.
So, why should you care? Well, because this giant magnetic field is basically our planetary force field. It's our shield. It stretches way out into space, and it deflects something called the solar wind, this constant blast of dangerous particles flying off the sun. That's what gives us the beautiful auroras, the northern and southern lights, but more importantly, without this shield, that radiation would have stripped our atmosphere away ages ago, and life on Earth would be totally impossible. It's that important.
Okay, we've already hinted at some of the differences between these two forces. But now, let's put electric and magnetic fields right next to each other, side by side, so we can get their unique personalities crystal clear.
So let's break this down. First, where do they come from? Electric fields. They come from charges, positive or negative, that can just sit there, and you can have one all by itself, a monopole. Their field lines start on a positive and end on a negative. But magnetic fields? Totally different story. They come from moving charges. You can't have a monopole, and their field lines, as we saw, are always closed loops.
But maybe the biggest, most practical difference is this one right here. An electric field will push or pull on any charge. Doesn't matter if it's sitting still or zipping along. A magnetic field, though, it couldn't care less about a stationary charge. It does nothing. It only puts a force on a charge that is already moving, and it just deflects its path. By the way, that little detail is what makes every electric motor in the world spin.
So, when you think about it, from shielding our entire planet from cosmic radiation to powering pretty much every piece of technology we use every day, electromagnetism is the force that truly shapes our world. It's this beautiful dance between electricity and magnetism, just woven into the fabric of reality itself. And that just leaves one big question, right? What are we going to build with it next?